Okay, no. So let's start discussing about like the actual application of iterative methods, including multigrid for unsteady PDEs. So let's start with two equations. Well, we all know how we can use multigrid to solve equations or iterative methods to solve equations like this, because we have been using this as the example of like our multigrid. So we already know, because these are discretized into AU equal to B, right? So now let's talk a little bit about how do we use multigrid to solve for unsteady equations. And I'm going to give two examples. One is partial u partial t equal to partial square u partial x square. And another example is partial square u partial t square equal to partial square u partial x square. One is a hyperbolic equation. This one is a hyperbolic equation. This one is a parabolic equation. Okay. So for this equation, we are going to we know we can discretize this into du dt equal to the same matrix A times u, and this one we can discretize as d square u dt square into this same matrix A times u. And we can, in our first two projects, we have been using an explicit integration method for solving this equation. But in many cases, it is beneficial to solve this equation using implicit methods. And when are these cases? When would you choose an implicit method to solve this equation, for example? Stiff problems, right? In ODEs, in an ODE like that, when the matrix A is stiff, that is when it is beneficial to solve this using implicit methods. And in our case, if A is a discretization of the second derivative operator, is this matrix stiff or not? Any ideas? If A discretizes the second derivative operator, is the matrix stiff or not? What do we mean by a matrix being stiff? It has some very large eigenvalues and some very small eigenvalues. Let's go to MATLAB and see if we have the case. So let's actually construct our matrix A, okay, without doing the Jacobi iteration, and let's close this and look at eigenvalues. Okay, it goes from minus 0.09 times 100 to about 240. That's not a very stiff matrix, right? And you probably know the condition number of a matrix. That is basically the largest eigenvalue divided by the smallest eigenvalue. It's 25. It's not a stiff matrix at all, right? 25 is very reasonable. But that's n equal to 8. Let's do n equal to 1,000. Construct A. An eigenvalue of A now goes from something with 5 zeros to, oops, it's a little bit too long, to basically something quite large on the order of 1, right? And if you type the condition number of A, it's now 4 times 10 to the 5. And as we discussed about the eigenvalues of the Jacobi iteration matrix, the condition number of this matrix goes like n squared. So when you have a fine grid, you get a very stiff system. So that's something interesting about PDEs, is that the condition number of the system, or how stiff it is, doesn't just depend on the equation. It depends on the grid. And in a lot of cases, it depends on the finest portion of the grid. For example, in aerodynamics problems, we ended up solving a lot of equations with, we ended up solving a lot of flow fields with boundary layers. That is a very thin layer near the boundaries of the domain. And in boundary layers, because of the large velocity gradient, we need a lot of grids to resolve the boundary layer. And as a result, this finest grid determines the whole condition number of the matrix. Like how small your grid has to be near the wall determines how ill-conditioned your matrix is. And this usually, if you have a very thin boundary layer, it's usually a lot better to solve the whole matrix using implicit methods. Okay, so if we use, let's say, the simplest implicit methods, backward Euler, to solve this, we are going to be using U of time step n plus 1 minus un divided by delta t equal to a times u of what? N plus 1. So that system, if you put all the unknowns, n plus 1s onto the left-hand side and the known onto the right-hand side, what we get is identity divided by delta t minus a times un plus 1 is equal to u of n divided by delta t. Right? So instead of a regular matrix like what we had previously, we get this matrix. We get the Poisson's equation matrix modified by an identity matrix. It's actually pretty interesting. If, let's think of a delta t to be really, really large, then identity over delta t is almost 0. Then we are going to be solving exactly the same system as we have been solving Poisson's equation. All right, when delta t is not that large, I mean, it's actually not going to be much different because it's just a modification of the diagonal. It doesn't affect the structure of your solver. It just affects the individual numbers of what you plug in. Okay, so all the methods we discussed, Jacobi, on the relaxation, Gauss-Seidel, multigrid, can be applied to exactly that. All right, let's also discuss this equation a little bit because we are going to be doing this in our project. This equation is discretized into d square u dt square equal to au, and if we define EV equal to du over dt, what we get is d dt of u and v is going to be equal to a matrix times u and v, right? And what is the matrix? We get 0 here, we get identity here, we get a here and 0 here. Okay, this matrix, let's take a look at the implicit solution procedure. The implicit solution procedure would be u of n plus 1, v of n plus 1 minus u of n, v of n is equal to delta t times this matrix times u of n plus 1 and v of n plus 1, right? And if you pull the unknowns to the left-hand side and known to the right-hand side, you would get something like this becomes un and vn. and the left hand side becomes identity minus delta t times identity, delta t times A, and identity. Oh, there is also a minus sign here. This matrix looks very different from the matrix we've been solving. Sorry, we have un plus 1 and vn plus 1. But it is actually pretty similar if you do a simple transformation. So that transformation is called the Gauss elimination. Okay, Gauss elimination on the block level basically tries to eliminate this term by left multiplying the matrix with a lower diagonal matrix. So instead of solving this equation, we are looking to solve an equation that looks like this: identity something, identity 0 times the matrix we have on here. So basically we are multiplying both left and right hand side by this matrix. And the purpose of this is so the product of these two matrices does not have this term. It's equal to the same matrix times un and vn. Okay, so I almost got to finish the lecture. So the question for you is, what question mark should I put here so that this product matrix does not have a lower diagonal block? Somebody said it. Sorry, I didn't. Question mark equal to delta TA, right? Good point. So this is basically Gauss elimination for 2 by 2 matrix. And if I plug in the question mark equal to delta T times A, you're going to find out that we are ended up going to be solving an upper diagonal block matrix. And the solution procedure for that matrix, again, would look pretty much the same as our discussion of solving the Poisson's equation. We can still use Gauss-Seidel on the relaxed Jacobi and multigrid to solve the same system. All right, so if you have questions on this or on any other things, project 1, project 2, or anything related to this or unrelated to this lecture, I'm going to have an office hour in building 33 on the first floor from now to 12 o'clock.